In this last video, we're going to look at the shapes of the orbitals. You're going to see the results of my drawings, and as I go through them, these are best practiced a lot. We can also take some time to look at different representations of these 90% probability shapes, but it's going to be really important for you to put, I don't know, pen to paper, pencil to paper, Apple Pen to iPad, etc., to practice drawing the shapes so that you are proficient at representing these things. So we're going to take a little art class detour. So a reminder that this is a 90% probability, right? There's a 100% probability that the electron exists somewhere in the universe, but we'd like to locate it a little bit better than that. There's a 90% probability that it is in this sketched shape that we're going to do. Some of these orbitals have nodes, and these are planes of zero probability, and they exist because nodes exist in waves, right? In a wave, there's a point at which it goes through zero to go from a positive amplitude to a negative amplitude. Now, we get the probability by squaring the wave function, but 0 squared is 0. So nodes will continue to exist even when we draw our probability pictures. When you draw orbital pictures, they must be drawn with respect to, that's what the WRT stands for, with respect to an axis system. I can go through, and I do here, and I can in class, what it looks like to draw the orbital on the axis system, but you are also welcome to draw it next to the axis system. So if it's easier for you to draw it without the axis lines, as long as you can make it look like it's pointing in the right direction, if it needs to point in a specific direction, that's what matters. You must shade them to indicate phase. So even though we're squaring this to get a probability, we're carrying over some wave characteristics, which is when you pass through a node, the phase changes, right? If it was just the wave goes from that positive amplitude to the negative amplitude, we're going to apply some shading convention to convey that. And you should be able to sketch these. Now for the s orbital, I'm going to go into through a few things so that you can see what it looks like. And in the very end, I will give you an example set of everything drawn off an axis system. So s orbitals are spherical. They don't have any nodal planes. Now there is something called a radial node that shows up in even s orbitals. They are important to a more sophisticated understanding of bonding that we don't have to do in Gen Chem, and you don't have to do it in Orgo. So we can build up to that, and if you are planning to go on and take things like inorganic chemistry, honestly, I would probably have a field day if you wanted to sit down and talk about radial nodes. So happy to do that, but it won't affect any of the bonding that we need to talk about, and it won't affect the bonding you need to talk about for organic chemistry. So if it's spherical, then there are no nodal planes. So no nodes means no reason to change phase. So the whole orbital is in the same phase. Now, drawing a sphere on a flat piece of paper is not that easy to do, because also since we're going to shade it to indicate phase, you can't do any shading to indicate 3D shape because it might accidentally indicate phase. So you can draw it as a circle. And your other option is to draw it as a circle and then shade it in. So the way that we will represent phase is that it is either shaded or unshaded. And it's not that one means positive and the other one means negative. It just means one is the opposite of the other. That's all that it is. So, it, right, shaded is the opposite phase of unshaded. Okay. Now I did say that we needed to do an axis system. I will always use this right-handed axis system where X and Y are in the plane of the paper, in the plane of the board, like a normal axis system that you would see, but we're working in 3D, so we need the Z axis. When it's like this, it means the positive Z axis would be pointing out toward you. Again, I mean, this doesn't really matter too much for a sphere, but to show you what that sphere would look like on an axis system, right? I've got that here with the orbital drawn in blue and 0, 0, 0, so the absolute origin is where the nucleus is, right? Everything is centered around the nucleus. So that's an s orbital. You'll draw it like a circle. It really means that it's a sphere. You can either shade it or unshade it. I would say that the majority of people choose to not shade their s orbitals, but both are correct. A p orbital. So, and then I've got a reminder here, right? 2p is the lowest energy p orbital that we will see. Because at n equals 1, you can only have L equals 0. So L equals 1 doesn't start until you get to n equals 2. So the p orbitals, there are 3 in the set because my m sub L values were -1, 0, and +1. Each orbital has 2 lobes. Each orbital has 1 nodal plane. And the way that we will label these, so right, one of them is +1, one is 0, one is -1. We're not going to assign those numbers to anything because it depends on a lot of other factors. What we are going to do is label them according to the axis that they sit on. Because when you draw the 3p orbitals, the way that the shapes turn out is that one points along the x-axis, one points along the y-axis, and one points along the z-axis. So here's what that looks like on an axis system. So I have my x and y-axis in the plane of the board. My p orbital, it has a node at the origin. It has, for my px, one lobe that points in the positive direction on the x-axis and one lobe that points in the negative direction on the x-axis. So this is the px orbital that is on the x-axis. The nodal plane goes right through the middle, right? So that's a 0 probability of finding the electron at the origin. So I shade one side and I don't shade the other, and it doesn't matter which side you shade. The py orbital is the exact same shape, but now pointed along the y-axis. So I have 0 probability at the origin, right? We're still centered on the nucleus. A lobe that points on the positive y, a lobe that points on the negative y, shade one, not the other. PZ, same thing, but along the z-axis. Especially for PZ, this is where an axis system might help you show the 3D representation of it a little bit better. But again, it will be totally up to you and how you can best draw it to communicate that information. The d orbitals, so now the lowest energy d orbital we can have is 3d. These have 2 nodal planes, and there are 5 of them. So there are 5 d orbitals to know the shapes of and be able to sketch and label. So the first 3, you're going to see this pattern here. There's dxy, which is in the xy plane. So I've got my normal axis system. I've kind of like just put a dashed line in for the z-axis so that we can just look at the axes for the plane that the d orbital is in. And it has 4 lobes. Each lobe points in between the axes, and it's like at a 45-degree angle, like perfectly in the middle of the axis system. Now, the way that the nodes work, this nodal plane is cutting through on the y. I mean, it's the zy plane is a node, and then the xz plane is a node. So, right, it looks like the shading ends up looking a little bit weird. Like it seems like maybe we did it wrong based on how we shaded the p orbitals, but the best way to figure out what you're doing when you shade a d orbital is to pick a lobe. So if I pick, I don't know, the upper right lobe, decide that it's going to be unshaded, and then just move either clockwise or counterclockwise. I'm going to clockwise, and then when you pass through a node, switch the shading. So right upper unshaded, if I go clockwise, I pass through one node to get the right lower. So now that's shaded. Keep going clockwise, and I've got the lower left unshaded. Keep going clockwise, I've got the upper left, and now that's shaded. So even though it looks like the lobes opposite each other, you did not apply the shading properly. When you go from one lobe to the one that it's perfectly opposite, you pass through two nodes. So it's like hitting a double negative. So you pass a node, so you change the shading, and then you pass another node, so you change the shading back, and that's why they end up with the same. So that's dxy between the axes in the plane of xy. So dxz is between the axes in the plane of xz. So I will have in the xz plane, right, which is like parallel to the ground, it's going to be like coming out, it's like perpendicular to the paper, coming out at you. A little harder to show the perspective, but you can see I've got my lobes in between the axes, and then I've also applied my shading. dyz is in between the axes in the yz plane. So this kind of like vertical coming in and out at you. Again, do the best that you can. If you're trying to put this on an axis system, I'll also show you how to draw these off an axis system. But YZ in the YZ plane between the axes. Then we get two kind of weird ones, and they're weird only in that, right, this was all solved mathematically. So they're labeled based on some sort of mathematical solution that pulled out these 5 shapes from the wave function and all the other information we had. So dx squared minus y squared. The good news is that it's in the xy plane, so that's easy to figure out. It's in the name to tell you where to put it. But now, instead of being between the axes, like we had for dxy, it's on the axis system. So a lobe pointing on the y-axis and positive and negative, and a lobe pointing on the x-axis, positive and negative, shaded appropriately. The last one is dz squared. So this z squared is a bit of an abbreviated form of the name, but it's good enough to point us toward the axis that we need to put it on. So I have rotated my axis system a little bit here. I've pointed the z-axis up so that we can draw this picture a little bit easier. What it looks like is it has a lobe pointing along the z-axis in the positive direction, one pointing in the negative direction, and then it has like a donut around it, or like an inner tube around it. So that's the shape. Which the more you think about it, the weirder it gets for electrons. So, right, I have 2 pieces here that are completely separated, but it is one orbital. So if I had an electron that I knew was in a dz squared orbital, there's a 90% probability that it's somewhere either in the donut or the lobes, but it can't be in both places simultaneously, because it's only going to be in one place somewhere in there. But also, there's a whole bunch of space in between that it can't be. So if it's moving around in this orbital, it has to get, yeah, you can just keep going and take all of the even more cool, in-depth, crazy quantum mechanics classes. I'm kind of glad that we don't have to deal with that, but it is super cool. Okay, so for this orbital, it does have the nodes in it that help you figure out how to do the shading. The short answer is that you are either going to shade both of the lobes or the donut. Usually easiest to shade the donut so that you can get a little bit of that 3D perspective, but it is entirely up to you. And the reason that it is either the lobes or the donut is because the nodes in the dz squared orbital are conical nodes. So they're no longer planar nodes. They just happen to be little cones, which is why we get the shading pattern we do. That is all of the orbitals on an axis system. I next have a set of pictures. So this is the full set of orbitals that I'd like you to be able to draw, shade, and label. I have them off the axis system. You can do whichever works for you, whatever makes more sense for you communicating the drawing as clearly as possible. So I have my axis system over to the left, and because of that, right, all of my orbitals will be drawn with respect to that axis system. I'm not going to rotate anything. So my dz squared is going to have to point differently than it did when I drew the axis system. Okay, my s orbital shape is a sphere. I'm going to draw it as a circle. You can shade it or not shade it. My p orbitals, I have a px orbital that points along the x-axis, py points along the y-axis, and pz points along the z-axis. Now for pz, you can still draw the perspective version, kind of like slanted. It should not look like x or y, like we did when it was on the axis system. Or you can imagine like the z-axis would be pointing directly out at you. So if I'm looking at a p orbital, I'm really just going to see like a circle for the top of it and then kind of like the back lobe pointing out. So that's the way I've drawn it here. For the d orbitals, dxy, xy plane between the axes, shade it. xz is the xz plane, so you would kind of see like the two lobes coming out at you and two lobes going back. dyz, you would see the same thing. I guess this one looks a little more like a chromosome, I guess, but right in the yz plane, kind of two lobes coming out at you, two lobes going back. X squared minus y squared pointed along the x and y axes, and then d squared, you've got, it kind of looks like a really big pz orbital with a donut around the middle.